Hello students. Last class we studied about what is the difference between order and molecular rate of reaction and what is the integrated rate equation for zero order reaction. Today we are going to study about integrated rate equation of first order. Integrated rate equation first order reaction. Okay, so what do you mean by first order reaction? So first order reaction is one where the rate of reaction depends on unit power of one concentration term. Unit power of one concentration term only. So this can be represented in various ways. Suppose it's given A give rise to product, or A plus A give rise to product, or A plus B give rise to product. Suppose different equations are given, but each case R is proportional to A to the power 1. R is proportional to A to the power 1. Although there are two molecules or two species of reactant species, but only depends on one. Or A plus B different reactant species and are proportional to A to the power 1. Different may be reaction, but if represented in this rate, if it depends on the unit power of, if the rate depends on this unit power of only one reactant term, then this is known as your first order reaction. This is first order reaction. Okay. Now let us consider a first order reaction where A give rise to product. There are different. Suppose this is given A give rise to product. Suppose the reaction is given A give rise to product, and initially we start with A moles of liter of A when time T equal to 0, and after some time, suppose the X moles per liter of A is consumed. Then T, when time T equal to T, so X moles per liter of this A is consumed and initially taken A moles. Then what is the concentration of A remain after time T? So the concentration now remains A minus X moles per liter. A minus X moles per liter. And what is the rate of reaction at that instant? So according to rate, or this dx by dt now proportional to A minus X. So this is the X moles of product is formed. In terms of product, the rate of reaction I have written dx by dt. So dx by dt proportional to A minus X to the power 1. Okay, to the power 1 means only A minus X. So dx by rate of reaction is proportional to this one. Or so rate that is equal to dx by dt, or so dx by dt equal to some constant k A minus X. So what is this k? This k is specific reaction rate or rate constant. Specific reaction rate and rate constant of this reaction. Just rearranging this equation, what we get? Or dx by A minus X equal to k into dt. Okay, now integrating. So we have to get the integrated rate equation. So now integrating both sides. Suppose this is your equation 1. Integrating both sides, what we get? dx by a minus x equal to k dt. Okay. So what is the value of this? Look here. So dx by a minus x, that is equal to derivative of this is minus ln a minus x equal to kt plus c, where c is constant called integration constant, where c is a constant, c constant called integration constant. This is integration constant. Okay, suppose this is equation number 2. So when t equal to 0, at that time when t equal to 0, what is the value of x? X equal to 0. So substituting these values in equation 2, what we get? Minus ln a equal to c. So minus ln a minus x, this term is minus ln a, and k into 0, that is equal to 0 plus c. So in this minus ln a equal to, so minus ln a equal to c. Now substituting this value of c in equation 2, substituting the value of c in equation 2, what we get? Minus ln a minus x equal to kt minus ln a. Now arranging this, or ln a minus ln a minus ln a minus x, ln a minus ln a minus x equal to kt, or kt equal to ln a by a minus x. This is equation 3 and this is equation 4. Okay, so kt equal to ln a minus x. You know this ln is to the logarithm to the base e. Suppose we convert it to logarithm to the base 10. Then what happens to this equation? Then this equation becomes kt 2.303 log a by a minus x to the base 10, and this is equation number 5. Okay, or we can write k equal to 2.303 by t log a minus x. Suppose we put another equation 6. So these equations are known as integrated rate equations of first order reaction. So these equations are known as integrated rate equations of first order reaction. So this is in terms of ln to the base e, logarithm to the base e. This is logarithm to the base 10. This is the only difference. Ln a by a minus x equal to 2.303 log a minus x. Okay, so this is one equation, and another term we also express this in different way. Okay, so look here to this equation 4. From this Another way, suppose the initial concentration is taken. Suppose instead of A and A minus X, suppose the initial concentration taken A naught, and after some time the concentration of A, suppose A. After some time the concentration suppose A, and the initial concentration suppose A naught, then this equation 4 can be written as KT KT equal to ln A naught, KT equal to ln A naught by A, or this can be represented as e to the power KT. Okay, we can also write A naught by A equal to e to the power kt. E to the power kt e to the kt equal to a naught by a, or you can write a naught by a equal to e to the power kt, and just by changing it, a by a naught equal to e to the power minus kt. So these equations are also called integrated rate equation for first order reaction. That is equation 7, and this is equation 8. So these equations are also known as integrated rate equations of first order reaction. Okay. So next come to what is half-life period. So remember these equations. Okay, I am writing here A naught by A equal to e to the power kt, and another form reciprocal of this A naught by A equal to A by A naught equal to e to the power minus kt. Okay, so these are the different equations. Next come to what is half-life period. Half-life period of first order reaction. Half-life period of first order reaction. Okay. So what is half-life period? The time period during which the half of the reactant consumed from its initial concentration. So the time during which half of the reactant consumed, or half of the reaction is completed, or half of the reactant is consumed from the initial concentration, that is known as your half-life period, and represented as what? T half. So at that time T half, if the half of the concentration is consumed or half of the reaction is completed, then suppose the initial concentration is A moles per liter, and at that time what is your X? So X value equal to, at half-life period, X equal to A by 2. X equal to A by 2 moles per liter. Okay, substituting these values in equation 6, in this equation 6, substituting these values in equation 6, what we get? We get K equal to 2.303 by T half log A by A minus A by 2, that is equal to 2.303 by T half log A by 2, that is equal to 2.303 T half log 2, that is equal to 2.303 value, that is 2.303. Okay, given, see 2.303 and log 2 value 0.301 by t half. So when we multiply these two, so what we get? Here we get 0.693 by t half. So k equal to 0.693 by t half, or what we can write, t half equal to 0.693, just by changing this, t half equal to 0.693 by k. So this is the relationship between rate constant and half-life period. This is the relationship between rate constant and half-life period of a first order reaction. Okay. So what relation here we get? T half equal to 0.693 k. So these equations are important. In this way I have kept here. And this is also another equation, that is T half equal to 0.693 by k. So this is the relationship between half-life period and rate constant. So what we get? T half 0.693 by k. Okay. Next, what is the characteristics? Characteristics of first order reaction or first order kinetics. So first, any equation which is of first order, that should obey these equations. Any equations of first order, that should obey equation number 4 and equation number 5, 6, etc. So which one is applicable according to that? Not 5 is not a true equation. So any equation, any reactions of first order, that should obey these equations and this equation, equation number 4 and equation number 6. That should obey equation number 4 and 6 and these equations. And the half-life period is here independent of initial concentration or concentration of the reactant. It only depends on rate constant. And what is the unit of rate constant? Here the unit of rate constant is, so look here, k 2.303 log a by a minus a. This is one concentration unit, this is one concentration unit. So as this is the division of concentration unit in this way, and time is here. So in this way the unit of rate constant is time inverse. That may be in second inverse, minute inverse, hour inverse, etc. They may be in different way, but the unit is time inverse. So any reaction which of first order, that should obey this equation. Okay. So another equation I have given here, Kt equal to so also obey this equation, and T half is independent of initial concentration and unit of rate constant is this much. Okay. Next come to graphical presentation of this first order kinetics. Graphical presentations. Okay, so look at this equation number 6. So, or equation number 5 even, Kt equal to 2.303 log a by a minus x. From that equation we can write Kt by 2.303, Kt by 2.3 equal to log a by a minus x. So Kt 2.303 log a by a minus x, or Kt by 2.303 equal to log a minus log A minus X. Okay, or this implies that log A equal to kt by 2.303 log kt by 2.303 plus log A minus X. Instead of A, I can write here A naught instead of A. Log A equal to kt by 2.303 log A minus X. Then what happens here? Suppose this is the variable, this is the constant term initially, this one the constant term. So in this way what happens? When we draw this equation can be written log A minus X. Suppose log A minus X, this side comes here, it gives you minus kt by 2.303 plus log A. Okay, suppose this term comes here, it becomes like it, and I have just rearranged. So log A minus X equal to minus kt by 2.303 log A. So when a graph, so this is variable and this one is variable and this is a constant term. Initial concentration, this is a constant. So here, so suppose the graph is plotted log A minus X versus time t, concentration term log A minus X here and time here. Then what happens? This is the same way as that of the equation of straight line y equal to mx plus c. This is the intercept here and this graph will be like this with slope minus equal to minus k by 2.303. So by drawing the graph between log A minus X versus time, we can find out the slope. From that we can find out what is the value of rate constant k. So the rate constant can be drawn from this graph. Okay, and by substituting the concentration term at different times, this value of k can also determine. Okay, so this is the equation. When a graph is plotted log A minus S versus time, it gives a straight line with intercept. This is the intercept, that is log A, and the slope equal to minus k by 2.303. Another equation also given. What is that another equation? Log, look here, kt by 2.303 log A by A minus X. kt by 2.303, if the graph is plotted according to this equation, we get graph like this. And when the graph is plotted kt by 2.303 versus log A minus. So suppose the graph is drawn between log A by A minus X versus time. Log A by A minus X versus time. Then this is also equation of straight line. Here no intercept and it gives a straight line passing through the origin. It gives a straight line passing through the origin. Okay, and with slope equal to k by 2.303. So when graph plotted versus log A minus X versus t, it gives a straight line passing through the origin with slope k by 2.303. And when graph is plotted log A minus X versus t, then it gives a straight line with intercept log A and slope minus k by 2.303. Similarly, another equation here given, t half equal to 0.693 by k, as t half equal to 0.693 by k. So when the graph is plotted, here we have taken suppose the concentration term and here we have taken the t half. Whatever may be the value of the concentration, always the T half depends on K, as K is a constant quantity. You know the rate constant for a particular reaction at a particular temperature is constant and is a constant quantity. In the same, T half is a straight line parallel to concentration axis. This is the T half versus concentration graph. This is log A into A minus X versus time graph, and another graph that is log A minus X versus time graph. Okay, so the first order reaction has a different graphical presentation. Looking at this graph, we can also identify what is the type of reaction. And what are the different characteristics? Now you know what is first order kinetics. Now you know how to find out this K value. You know. Okay. So for today up to this, in next class we will discuss some numerical problems.